Welcome to the surface physics presentation. In this talk we will cover the surface layer and the land and water surface treatments in the model, which are the SF-SFC lay physics switch and the SF surface physics switch. The surface interacts with all the other physics in the model. Rainfall from the microphysics and cumulus scheme drive the surface and soil moisture. The radiation, of course, drives the energy budget, and the main output of the surface is the surface fluxes, which would be the latent heat flux and the sensible heat flux, and also its effect on momentum through friction. So we'll cover all these processes during this talk. So the surface of the model, it really is in two parts. One is the surface layer of the atmosphere, that provides some diagnostic fields that are needed by the land surface model, called the exchange coefficient. And then the land surface model itself, which has a soil moisture, a soil temperature, a snow prediction scheme usually, and it also may include a sea ice temperature. This shows how the surface layer interacts with the land surface model and in some cases directly with the boundary layer scheme itself. The main purpose of the surface layer scheme is to provide the exchange coefficients of heat and moisture to the land surface model. The land surface model can then use those to provide the fluxes of heat and moisture to the boundary layer. Friction is handled directly between the surface layer and boundary layer. The surface layer provides a friction stress term, which then acts as a lower boundary condition for the momentum in the PPL momentum mixing. So these are the three components of the surface part of the physics. So this talk is about the first two, the surface layer and the land surface model. The surface layer physics has several options. It's usually related closely to the PPL scheme. So you'd have to refer to the table that links the surface layer scheme to a particular PPL scheme. But all the surface layer schemes are doing the same basic thing. They use similarity theory to determine the exchange coefficients and also the diagnostics needed for the 2-meter temperature and moisture and the 10-meter winds. So they provide the exchange coefficients to the land surface models. They provide friction velocity to the PBL scheme. They provide surface fluxes over water points where the land model doesn't operate. And the schemes have variations in the stability functions and roughness lengths. The surface layer is a thin layer near the surface, about 100 meters thick or a tenth of the PBL height, and it's a layer where the flux is assumed to be constant and follows similarity theory. The lowest model level is usually within that layer, and it's because it is typically 10 to 50 meters above the ground. So the lowest level variables can be used to derive the surface fluxes via similarity theory. The similarity theory is basically an assumption about the profile through the surface layer. An example is the heat flux, which is given by rho Cp U star theta star. In similarity theory, U star and theta star are constant in the surface layer. And there's a roughness length as well, which I'll come to later. So this diagram shows the surface layer of the model and the lowest model level here in red, the red point, which has a velocity at the lowest model level and the height of that level, c1. So similarity theory says that the velocity goes as a log of z. Notice there's a log profile on the axis. So the velocity is linear with log z and has an intercept at z0, the roughness length. And the gradient is u star over k. So this u star is a constant in this layer, and it can be related to both v1 and z1 through this formula, which gives u star as a function of the lowest level velocity and the height of the lowest level if the roughness length is known. So similarity theory has this relation between the velocity and the height. It's basically a log function of height with a constant gradient in the neutral case. The roughness length, Z0, is a measure of the initial length scale of surface eddies and generally differs for velocity and scalars. It depends on the land use type and is an input parameter for the model based on the land use. So for higher obstacles, they have a higher roughness length. Things like trees in urban areas would have roughness lengths up to 50 centimeters or a meter, for example. Grassland may have a roughness length of about 1 centimeter. So it depends on the input land use category of the grid cell. It may also have a seasonal dependence, for example, cropland or even forests. Some schemes use smaller roughness lengths for heat than for momentum. That's called a thermal roughness length when the heat value differs from momentum. For water points, the roughness length is a function of wind speed to represent the effect of waves. But typically over water, roughness lengths are very small, of the order of millimeter to maybe a centimeter in extreme cases. So now we come to the surface fluxes. The heat flux is given by rho P U star theta star, the moisture flux is given by rho U star Q star, and the momentum flux or surface stress is given by rho U star squared. Recall that U star is a constant in the surface layer and defined by the lowest level value of velocity and this log profile. But now we also have this stability function psi m. In neutral conditions, psi m is 0. In unstable conditions, it's positive, and in stable conditions, it's negative. So in unstable conditions, U star is enhanced by this denominator with the psi m, and in stable conditions, U star is reduced. So the stability impacts the values of U star and theta star in similar ways, and Q star. So all of them are related to the lowest level, but in the case of theta and Q, it's the lowest level minus the surface. And we don't yet know the surface theta, which is the skin temperature, and similarly we don't really know the surface moisture. And we won't know any of those until we've run the land model. So we don't know enough for the heat flux yet, but we do have U star. So this is used in the computation of the land model to come up with the fluxes later on. So the stability functions we saw in the previous formula are defined here. The stability function is a function of z over L, where z is a level and L is the Monin-Oberkopf length. So z over L actually has this definition, given the definition of the Monin-Oberkopf length. And it's a function of theta star and U star. It's also related to the Richardson number. This is how the Richardson number is defined. It's a function of the temperature difference divided by the wind speed squared. And we can calculate the Richardson number, at least from the previous time step value of the delta theta and the wind speed. So we know the Richardson number, and then this bottom formula relates the Richardson number to z over L. But note that z over L appears in several places, so this is going to have to be an iterative calculation to get z over L from the Richardson number. So, as we mentioned here, z over L is obtained from the Richardson number via iteration in the revised surface layer scheme, which is one of the popular options in WRF. But typically, you do have to find a way to define z over L before you can get psi. The stability functions themselves are given here in graphical form. The unstable function is positive, and as a function, so psi is a function of z over L, and this is the value over a large range, and this is the same function over a smaller range. But you can see that it basically increases as z over L becomes more negative, and these are unstable conditions when z over L is negative. For stable conditions, z over L is positive, but psi is negative. So this is, in these formulas, the grey line refers to the one we actually use in WRF. So the grey dashed line for the stable and the grey solid line for the unstable. This again shows the formulas in the revised MM5 similarity theory, but they all look very similar to this. The stability functions are fairly traditional parts of similarity theory. There's also a momentum and a heat version of similarity functions, and they also look kind of similar. Again, unstable conditions on the left and stable conditions on the right. So to get the heat flux, we need to know the exchange coefficient. The exchange coefficient is the ratio of the heat flux to delta theta, and we call it CHS in WRF. And CHS is therefore given by this formula. In fact, when you relate this to the previous formula for the heat flux, it's only a function of U star, the roughness length, and the stability function for heat. So this exchange coefficient is needed by the land surface model to be able to compute the heat flux, because the land surface model also computes the surface temperature that's required for this delta theta. So the input to the land model is CHS, and the output of the land model will be the heat flux and the skin temperature, which will give delta theta, to agree with this formula. Before going to the land model options, I'll talk about a few other options related to the surface of the model. We have hurricane options. One is an ocean mixed layer model, which is a 1D slab ocean mixed layer with a specified initial depth, and it includes wind-driven ocean mixing for this, which will give you the sea surface temperature cooling feedback. And it's an important feedback for hurricanes sometimes, when you have a shallow mixed layer that will cool quickly in response to strong winds. So the ocean mixed layer model is mainly for that purpose, is to provide a feedback of mixing in the ocean due to strong winds. We also have a more full ocean model called the 3D BWP ocean from the University of Miami, which is a multi-layer ocean with, you can even have 100 levels, that even includes salinity effects but has a fixed depth. So it's not really a full ocean model in the sense of having bathymetry, but it captures most of the three-dimensional features you may need. It's also developed mainly to look at open water interactions between hurricanes in the ocean, for example. So that's another available ocean model we have. Of course, you wouldn't initialize, we don't have initial currents for this, so it would be initialized with no current and assume that the hurricane-driven winds are the main force there. We also have alternative surface layer options for high wind ocean surfaces called ISF TC flux, TC being tropical cyclone, mainly designed for use with hurricanes and with the surface layer option 1. These modify the Charnock relation, which is the relation that relates the roughness length to the wind speed for strong wind conditions. And in fact, the modification is to give less surface friction at high winds because the Charnock relation gives you too large roughness length compared to hurricane strength, observed roughness lengths. We also modify the surface enthalpy for heat and moisture fluxes, either with the constant roughness length for moisture or with the Garrett formulation, which is another way to compute the denominator of the exchange coefficient. So these are options especially for hurricane conditions. Also, we go to fractional sea ice. We have ways of dealing with that in the model. If you have a fractional sea ice input, which sometimes you may have, we can handle that in WRF by having a partly open water and partly fractional sea ice area. So it maintains that fraction, and the fluxes vary according to what fraction is open water. So basically it calls the surface layer twice, once for the ice part and once for the water part, and computes separate fluxes which it then combines. So now we come to the land surface models. These are given by the SF surface physics switch in the name list. We have the simple 5-layer soil model that's not used much except for idealized cases. Most of our usage is with a full land model. So we have the NOAA LSM, NOAA MP, which is the newer version that's currently being developed. RUC LSM, the Plime-Shoe, CLM4, which is from the climate model, Simple SIB, which is also a climate model, land surface model. This is an illustration of some of the land processes. Over land, we're dealing with sensible and latent heat flux and the ground flux, and then it's balanced. There's a radiation balance with the long wave and short wave. So basically there's an energy balance at the land surface. There's also a moisture balance based on the rainfall and the drainage of water into the soil. And below ground we have the soil layers. Typically there may be 4. And then in each of those there's a temperature and a soil moisture. And then also some land models predict snow cover as well. So there will usually be a snow model. It may be multi-layer in some cases. WRF also has to deal with water surfaces, and those are usually just constant temperature unless we're using one of those ocean options that I mentioned before. And there the surface layer scheme directly provides a sensible and latent heat flux. But when you're running a land model, the land model has to provide these fluxes as part of its output. So a land surface model has to deal with quite a lot of processes, and it's complicated by vegetation. So in addition to snow here, we have vegetation, we have multiple layers, root zones which can take water from deeper layers, and evapotranspiration which can put that water out into the atmosphere. So there's roots from deep soil moisture into the atmosphere via vegetation. And the vegetation also responds to the diurnal cycle and other forcings which control the evapotranspiration. And so there's some complexity introduced by vegetation, where you can have latent heat fluxes that are not just due to the ground difference from the air moisture, but also due to what the vegetation is doing. We also deal with runoff on the surface and a deep water runoff that the land model will produce from the excess rainfall. Without a hydrology model, the runoff just is assumed to go to rivers. With a hydrology model, this runoff will actually be input to a hydrology model. So the land model is driven by surface energy and water fluxes. It predicts soil moisture and soil temperature in 4 layers. For NOAA or NOAA MP, RUC has 9, Plime-Shoe has 2, Simple SIB has 3, and CLM4 has 10. So different numbers of soil layers, different depths. Predicts snow water equivalent on the ground, or it may have that in layers as well. And it can predict either canopy moisture alone or canopy temperature alone, or both, depending which option you've chosen. So these are the land surface options in WRF. There's the 5-layer slab, which doesn't deal with soil moisture at all, just temperature. Then there's the more sophisticated land models, with NOAA MP being the currently developed version at NCAR. This shows some characteristics of the land models. They have different numbers of soil temperature layers, different numbers of soil moisture layers, which are typically match the temperature layers, and then the snow layers. Like NOAA only has 1 snow layer, but NOAA MP has 3 snow layers. So that different levels of sophistication there in how they treat the snow prediction as well. The vegetation and soil, the processes include evapotranspiration, the root zone and leaf effects. The vegetation fraction varies seasonally. That's an input data set. So it's a monthly global data set that is passed from the GeoGrid stage all the way through to WRF. We consider vegetation categories in the land use types, and soil categories as well, which affect the drainage, for example, and the thermal conductivity. And all of this information comes from the GeoGrid program as global datasets. Land surface models include fractional snow cover and can predict snow water equivalent and how it develops based on the precipitation, sublimation, melting, and runoff. There's multiple ways of doing that depending on which option you've chosen. Multi-layer snow is included in the RUC, the NOAA-MP, the Simple Sieve, and the CLM4. There's also frozen soil water in some of these models, so it deals with the freezing of soil water, which has its own latent heat effects. The land model also comes with urban models. If you don't run an urban model, there's an urban category, which is just another land use category. So that's adequate for large-scale studies where you're not resolving urban areas very well, or you're not interested in them. If you are interested in urban areas and you're resolving them well, we have 3 different urban options. The urban canopy model, the building environment parameterization model called BEP, and the building energy model called BEM. Those are different levels of sophistication. These two, BEP and BEM, have multi-layer buildings, so they can actually exceed the lowest grid level, and the PBL scheme will allow for that in some case if you choose the right options. Building energy model also includes internal energy from things like heating and air conditioning systems, so it's quite sophisticated, and you can investigate much more detailed urban effects using the building energy model. These urban models can use quite complex variability between urban area types. For example, street width, roof heights, urban density. Those can vary in a map. And there's some efforts, one including NUDAPT, which has a map for 40 US cities. There's a more global effort called WUDAPT, which also gives you detailed maps. And in these cases with BEP and BEM, you can directly ingest the map information to the urban model. But the more default method is to just use the urban category. And we do have, at least for North America, we have the 3 categories simple map that can come from the GeoGrid stage. So the land surface models have tables so that you don't have to go into the code to change constants or parameters. Depends which land model you're using, which tables you want to edit. And these are text files, so it doesn't require recompilation. Veg palm table is used by NOAA and RUC for the vegetation category properties, such as albedo, roughness length, emissivity, and vegetation properties. MP table is used by NOAA-MP for a similar set of properties. Soil palm table is used by NOAA and RUC for the soil properties. And land use table is used only by the 5-layer model, and herb palm table is used by the urban models. All land surface models, except for the slab option, require additional fields for initialization. You need the soil temperature, soil moisture, and snow liquid equivalent. And these are in GRIP files, but they are not from observations. They come from offline models driven by observations. And they're often part of operational analysis datasets that you may have, or reanalysis systems. So you can get soil data, but be aware that these are coming from models that are driven by observations, but not real measurements in the soil. So some of these offline models are NOAA-like, or very close to NOAA, and will even have the same layers as NOAA does, the same 4 layers as NOAA and NOAA-MP. So they're consistent in the sense of having the same layers and also a lot of the same physics. And this lists some of the data sets here that would include those 4-layer soil and temperature and moisture options. There's also RUC data set, but it has limited availability for the RUC land surface model. We can use European Centre in ERA soil analyses. Real.exe interpolates those to the WRF soil levels depending which land model you're running. So the European Centre has different levels, maybe 7 levels. So we can interpolate vertically, but it doesn't really do anything else except interpolate it, even though it's a different land model. We don't try and allow for that. But even if you have a consistent land model, the resolution of the mesoscale land use means that there will be inconsistencies in elevation, soil type, and vegetation for a given grid cell in your model compared to the analysis. But the only adjustment we actually do is for the soil temperature, which we can adjust for elevation because we know the elevation of the original data set from the soil height data that comes in with MetGrid, from the MetGrid table, which it comes from the same place as the soil data. So soil height is the original height, and we do just an elevation adjustment for soil. That's the only adjustment we actually can carry out. But there is an inconsistency that leads to spin up as the adjustments occur in the soil temperature and moisture at the beginning of the simulation. The spin up can only be avoided if you want to run an offline model on the same grid for a long period, which may take months to spin up the soil moisture. We have offline models like HurlDAS for NOAA, where you can run it driven by observations for a period before the period of interest. An alternative is to cycle the land state between forecasts, which also helps, but also propagates errors. If you have rainfall in the wrong place, the soil moisture will be in the wrong place in the next cycle. So it's always advantageous to either use an analysis soil moisture, which has been driven by the correct rainfall, or use HurlDAS to spin up, and somehow HurlDAS has already got the correct rainfall as well. We also have a subgrid mosaic option in some cases. So NOAA has a subgrid mosaic option, and also RUC. This allows multiple categories within a grid cell. The normal running of our land models, we have one dominant vegetation per grid cell. So, but if you do want to have multiple categories allowed, then these mosaic options allow for that. Plime-Shoe also averages the properties of the grid category, so it treats them all as one, but it takes an average property. I didn't mention here that CLM4 has also capabilities for multiple categories per grid cell, but it takes in special initialization to use CLM with that. So currently when we run CLM, we just have one category per grid cell. Sea surface update is an option you have that you usually would want to use if you're running a long simulation of a week or more, which allows the sea surface temperature to change with time, because we do not have a prognostic sea surface temperature, we just have a specified value. So for long period simulations, you can read in the sea surface temperature as the model progresses, as the simulation progresses, and this is what's needed in regional climate simulations, for example. Sea ice is also updated at the same time. These fields are put into the WRF input file when you run real with this switch turned on. And they're coming from the same place as your meteorological data. They're coming from the MetGrid files, but they're put into this WRF input file, which is a time-dependent file that the model can read as it runs. The vegetation fraction is also read in during that because it's a monthly data set that also changes slowly. And the vegetation fraction, when you're running NOAA, the vegetation fraction will allow seasonal changes in the albedo, emissivity, and roughness length because those are scaled according to the vegetation fraction. Another way of changing albedo during long simulations, or even to set the initial albedo, is to use a monthly albedo input file, which is directly from satellite data, as opposed to having albedo as a function of land use. You can have this satellite-based one, and that's this useMonAlb equals true switch. The satellite monthly albedo then can also be updated with that switch during a long run. Also, when you're doing regional climate, you can set the TMN update, which is the deep soil temperature. Typically, the deep soil temperature is a fixed value. It applies to a 2 or 3 meter depth where the annual mean stays constant. So the value we use is just an annual mean temperature that comes from the geogrid stage, adjusted for elevation. But when you're running long simulations, we would like that to be able to update with a warming world, for example. So TMN update allows you to do that. And it uses something like 150-day average surface temperature to update the deep soil temperature. SST skin is a way of adding a diurnal cycle to sea surface temperatures. So it has a physically based model at the sea surface, which will allow for it to react to radiation changes, for example. It's a small diurnal cycle, but it allows that capability. Bucket M and Bucket J are more accurate ways to accumulate water and energy for long-run budgets. I'll describe them in the next slide. Output diagnostics equals 1 is an ability to output the maximum, minimum, mean, and standard deviation of surface fields in a specified period, for example, daily. So it's a way to capture your maximum temperature every day and minimum in one file, one daily file, so as opposed to having to search through all your hourly outputs, for example. Useful capability for regional climate. So accumulation budgets, when you're doing very long simulations, we have these accumulation fields, the rainfall and the accumulated long wave and short wave, for example, budgets. And the rainfall is in millimeters since the simulation start, and these budgets are also since the simulation starts in joules per square meter. So to capture the average over a period, you would have to subtract one from the other, the end of the period from the beginning, and then divide by the interval. And that'll turn this to watts per square meter, for example, or millimeters per day, whatever units you want to use. So for regional climate simulations, and we typically run WRF with 32-bit accuracy, we're adding small time-step values to accumulated totals, which can be quite large. And 32-bit accuracy only carries about 7 significant figures. So after a while, you start adding very small numbers to very large numbers and not actually retaining the accuracy. So the way we get around that is to have these bucket options, bucket MM and bucket J. They carry the total in integer and remainder parts. So you have the remainder in rain C and then the integer part, which is I rain C times bucket MM, and that's your name list option that you can specify the value of. So every time it reaches this bucket value, it'll tip the bucket and add an integer to this I rain C. And so when you want the total, you have to add rain C to this I rain bucket tip number times the bucket size. And the typical values that we'd recommend would be the monthly accumulations. So you'd set bucket MM to 100 millimeters and 10 to the 9 joules. Those are typical monthly accumulated values for these in regional climate run. We also have a lake model. The one we have in WRF is a 10-layer lake model from CLM, which is turned on with the SF Lake Physics equals 1 switch. We have global bathymetry data from GeoGrid that can come through to WRF and give the depths of most large lakes. Other lakes you have to use a default depth. The lake model can also predict lake ice, and it can be used with any land surface model. The WPS preprocessing allows a diurnal averaging method to initialize lake temperatures, because we don't really want to initialize them with an instantaneous 0Z or 12Z temperature, which may be either too hot or too cold. You'd ideally want to use a diurnal average temperature over a period, which is more typical of what a lake temperature would be. So we can initialize lakes using this T-average surface option available from the WPS. If you didn't have this, you could also use the SST, but if the SST didn't apply well over the lake area, it's not clear what value you would have there. We don't deal with WRF Hydro in this tutorial, but there is a whole model called WRF Hydro, which is a hydrological model that can be coupled to WRF or run offline. It does streamflow prediction. It does subgrid tiling to a 100 meter grid, which is required for some hydrological flow calculations. And it requires special initialization hydrological data sets. But it is coupled to WRF, so you can run a WRF Hydro coupled model. So that finishes the land model part and the surface layer. So the surface layer, as I mentioned, is interacting with the radiation and the rainfall, which drive it in terms of the energy, and then it also provides important fluxes to the boundary layer. The land surface model provides the sensible and latent heat flux, and the surface layer model actually provides the momentum flux or the surface stress.